Hi, it's Mrs. Sweck. I'm going to walk you through the Fluid Power Introduction PowerPoint. The primary components and principles of fluid power systems allow people in industry and machinery to achieve a lot of different tasks. Although fluid power has been used throughout history, it's far from obsolete. In fact, fluid power provides exceptional power advantages. Fluid power technologies impact areas like commercial farm machinery and respirator equipment that's used to provide oxygen to medical patients. Fluid power possesses some really important characteristics that we need to learn about. Fluid power has a lot of power per unit volume or mass. This is usually called power density. Fluid power systems are able to multiply force. And another advantage is that fluid can change direction quickly without damaging the system. This allows engineers and designers to utilize flexible piping and hoses so they can transfer liquid in a variety of directions. So in this lesson, you're going to be introduced to both pneumatic and hydraulic power. You'll learn the basic components of each system and how the systems are designed to manipulate work and power. And you should be able to see some connections between the other units that we discussed, power and work. The things that you need to focus on are that fluid power systems are categorized as either pneumatic, which uses gas, or hydraulic, which uses liquid. Fluid power is possible because in a system of confined fluid, pressure acts equally in all directions. That's a basic concept of fluid power. The most basic components of all fluid power systems include a reservoir or a receiver, some kind of a pump or compressor, a valve, and a cylinder. And you need to pay attention to that because that's what you're going to be sketching a diagram of for part of your homework assignment. Fluid power systems are designed to transmit force over great distances. They are designed to multiply an input force and increase the distance that the output can move. Laws about the behavior of fluid systems and standard conventions for calculating values within fluid systems help in the design and understanding of the system. And we use standard schematic symbols and conventions to communicate our fluid power designs. And you'll see some of those symbols and schematics at the end of the PowerPoint. Fluid power is the use of a fluid to transmit power from one location to another. Hydraulics, as I said, use a liquid flowing under pressure to transmit power. And pneumatics use a gas flowing under pressure to transmit power. So why do we use it? We use it for a lot of different reasons. One of the main reasons is that it multiplies and provides a variety of controlled forces. Outputs can be very closely controlled and they can provide a large amount of power. It's very easy and accurate to control, so you can start and stop, accelerate, decelerate, go in reverse, or position large forces with great accuracy. Think of something like the long arm of a big excavator or front-end loader moving big loads. There's one power source which can control many operations. It has a very high power, low weight ratio, which means high horsepower and a low weight ratio. Pneumatic components are compact and they're very lightweight. You can hold a 5 horsepower hydraulic motor in the palm of your hand. It has very low speed torque, so large amounts of torque force can be created at much slower speeds, unlike a normal electric motor. Constant force and torque outputs experience very little fluctuation. And it's very safe to use in hazardous environments, things like chemical plants, mines, anywhere near explosives, in paint applications, because it's really all of the fluids are spark-free and they can all tolerate very high temperatures. The basic fluid components, as I said, are the reservoir, which stores the liquid or the fluid, the conductors, which would be pipe, tubing, or hosing that allows for flow, your compressor or your pump, which converts your mechanical power to fluid power, and your valve, which controls the direction and the amount of flow. And then you have an actuator, which converts your fluid power to mechanical power. That's the thing that pushes or pulls. Here's some examples. For your homework, I'm asking you to come up with 4 examples of fluid power machinery, and I don't want you to use any of the ones that you see here in the PowerPoint. I want you to come up with some others. Let's talk about the physics a little bit of fluid power. Energy, as you know, is the ability to do work. Energy transfer goes from the prime mover, or the input source, to an actuator or an output device. Work as you know, is force multiplied by distance, and in this case it's going to be measured in foot-pounds. So how much work is completed by moving this 1,000 pound force 2 feet? You multiply it, force times distance, so it's 2,000 foot-pounds of work. Power is the rate of doing work, so it's work over time in seconds. So you take your work and you divide it by how much time it takes. So how many units of power are needed to lift a 1,000 pound force 2 feet in 2 seconds? Here's what your formula looks like. It's 1,000 pounds of power times 2 feet divided by 2 seconds. Or, whoops. Okay, horsepower. Hydraulic power is given by power equals flow times the pressure drop. Horsepower is the common unit for power, and 1 horsepower equals 1,714 gallons per minute multiplied by PSI, pounds per square inch, or pressure per square inch. So if you were going to calculate the horsepower provided by the system below, you're trying to lift 1,000 pounds of force, and you want to lift it in 3 seconds. So you take the 10 gallons per minute. Going back here, you can see that's your flow, and then you have your pressure drop. So it's 10 gallons per minute times 1,500 pounds per square inch divided by your constant, which is your horsepower, which is 1,714. In this case, your output is 8.75 in horsepower. Heat is the law of conservation of energy, and it states that energy can never be and it never change form. It can neither be created or destroyed. I'm sorry. It states that energy can neither be created or destroyed, but it can change forms. You should also know this from physics class. Energy not transferred to work takes the form of heat energy. So if you're not using it for work, to do something, it takes the form of heat. Torque is a twisting force, force times distance, and it's measured in foot-pounds. And this should also look familiar to you, but to calculate the torque produced by a 10-pound force applied to a 1-foot-long wrench, you take the force and multiply it by the distance. Torque is the twisting force applied by a hydraulic or a pneumatic motor, and your motor RPM at a given torque specifies power usage or whatever horsepower unit is required. Flow is what makes the actuator operation possible. So if you're looking at this schematic, you can see that there is an actuator located right over here, and that's what's pushing your force. So to extend the cylinder, flow has to be directed into port B. So the fluid comes in here and pushes the actuator forward. To retract the cylinder, flow has to be directed from which port? The answer is port A, so you need to put some fluid back here into port A, and it will push the actuator back. The rate of flow determines the speed of your actuator. It's measured in gallons per minute, and it's always generated by some sort of a pump or generator. With a given flow rate, actuator volume displacement directly affects the speed of the actuator. So the less volume you have to displace, the faster the actuator can move. Will the actuator illustrated below travel the same speed as it retracts and extends if there's a constant flow rate? No. The actuator will travel faster as it retracts because there's less volume caused by the shaft. Pressure overcomes the resistance to flow. Pumps produce flow by pressurizing the fluid. A pump can create greater pressure at lower flow rates. So if you restrict the flow from the pump, you get greater pressure throughout the system. All points of resistance in a series within a system contribute to the total system resistance. That means all your pipes, all your elbows, every single length that the flow flows through. Blaise Pascal invented the hydraulic press, and he also defined the relationship between force, pressure, and area. In this case, our units will be 1 Pascal equals 1 Newton per meter squared. And the formula equals force. The formula is force equals pressure times area. Just as a side note, the Earth's atmospheric pressure is 14.7 psi, which is equal to about 101,000 pascals. Pascal's law says that pressure applied on a confined fluid at rest is transmitted undiminished in all directions and acts with equal force on equal areas and again at right angles. So how much force is exerted on every square inch of this container wall? It's illustrated on the right. If 10 pounds of force is applied to the 1 square inch stopper, so here's your stopper, we're applying 10 pounds of force down, and remember the force is distributed evenly. The total resulting force acting on the bottom of the container will be 200 pounds of force. So you can see it takes very little pressure pushing down to create a lot of force. This is a diagram of a hydraulic press. Pascal's law is the basis for all fluid power that relies on pressure in a system. And these are the types of diagrams that you'll probably see on your test. This hydraulic press, it shows 10 pounds of force, can easily lift up 100 pounds. But what's your trade-off? The trade-off in this case is the distance. You'll notice that the 10 pounds of force has to travel this great distance, and it will lift this up a much shorter distance. This is what a schematic looks like. It's a line drawing. There's a lot of symbols and connections that represent the components of the system. These symbols are critical for technical communication. It's not dependent on language. It's just a symbol, so it's universal. It can be used all over the world. Here's some of the basic symbols. Here are some of the basic lines. This is all going to be in the PowerPoint for you to look at more closely. I'm not going to go over each one. These are the symbols for reservoirs. So this is a vented reservoir. This is a pressure tank, so it's completely closed. This tells you that the reservoir has a return line that's above the oil level, and this has a return line that's below. And this is a common reservoir symbol. These are symbols for pumps. These are symbols for control valves that control the flow. These are directional symbols. These are what we call check valves. These are the symbols for the motors. And these are the symbols for the cylinders, and you notice they have the actuators inside. So this is a single acting actuator. It's only got one line coming in. Here's a double acting actuator, so it moves forward and back, and it's got two lines coming in, and so forth. You guys can look at this PowerPoint on your own. And here's the resources. So what I'd like you to do, please, is just to get your homework done by Monday, and I'm also sending you the PowerPoint if you need to go back through the PowerPoint for anything. And I hope you guys have a great weekend.